So our next speaker is Semon Kirillovich Rezchikov from Symmetries, Floer Homology.
Thank you. So this is funny to talk a little bit about this here because I sort of started thinking about this stuff when Bargel Bott gave his Eilenberg lectures at Columbia when I was a grad student. This has some very distant connection to all that, but yeah, we'll get there. So, so suppose you have a symplectic manifold M with some symplectic form, and we're going to say it's sort of a nice symplectic manifold. So omega has a primitive. So it's an exact symplectic manifold. And so in that case, it's probably not compact, so maybe it's sort of convex at infinity. This is just condition for the not compact end manifold. So a fundamental study of object and symplectic topology, geometry is just Hamiltonian dynamics. So if you have a Hamiltonian function, then you get, well, many things. One of the things you get is you get a function on the free loop space of M called the action, which takes a loop to the integral of the one form over the loop plus maybe minus the integral of the Hamiltonian over the loop dt. Okay, so here Lm is the space of parametrized loops in your manifold. And you notice that the critical points of this functional, so this is some sort of function on an infinite dimensional manifold, and in some sense it's a smooth function, and you can sort of compute its critical points. Those critical points are the same as the fixed points of the time one flow of this Hamiltonian. So if you have a function like this, then you can use this to get, by solving Hamilton's equations, you get a diffeomorphism of your manifold. That's the Hamiltonian flow. And so people have studied. So this is a diffeomorphism. It's hard to study. This is a function. It's also hard to study. But it turns out to be, there turn out to be some properties of this function which are independent of this datum. So, maybe in particular, you might want some kind of count or some invariant of these fixed points, which doesn't depend on your particular choice of H. And so there is a sense in which that exists. This is a sort of fundamental object of Floer homology. So Morse homology. Maybe I'm going to do cohomology everywhere. H. So I'm putting this in quotes because it takes some work to define. But this is called the Hamiltonian Floer homology of H. And I'm going to denote it by HF star H. And you can put coefficients here if you want. But this is some homology group generated, just like in Morse theory, it's generated by the critical points with a differential counting the gradient flow lines. Okay, and then it turns out that HF H is does not change under compact perturbations of H. So,
perturbation with compact support.
Yeah, perturbation with compact support. So it depends a little bit on the geometry of H at infinity, but within any finite region, you change this however you want and it doesn't change its invariant. So that's useful. So in particular, for a compact manifold, well, it's a bit harder because this doesn't happen. So this is not a function, it's a one form. But in that case, it ends up being just independent of your Hamiltonian. So that's very useful. So let me give you an example of one setting where we know this quantity. So if you have M, this is like maybe one of the two fundamental examples. If you have a cotangent bundle and you have this of a Riemannian manifold, then there's the function norm p squared from the cotangent bundle to R. So this is the Hamiltonian for a free particle. And if you have a free particle moving around on your manifold, then HF T squared is the same up to some shift as the homology of the free loop space of your manifold. Okay, so that's a statement. And so maybe a warning, HF H is not, the homology of the free loop space of your manifold in general. This is some very special property of cotangent bundles. But there's a principle, a sort of algebraic structures related to the homology of the free loop space have analogs on Hamiltonian Floer homology. Okay, so for example, famously, this is a ring under this sort of a string product was introduced by Sullivan. You have a family of loops in a manifold, another family of loops. You intersect those families by concatenating the loops when like the marked points at zero touch. So. Okay, and here there is some corresponding related product, which takes the form of some count of pseudo-holomorphic pairs of pants with some perturbation term. Okay, so these are both rings. And the general principle is that whatever you have here happens here, maybe with some mild modifications. So that's very interesting.
Are these products too?
That is a theorem that here was proven somewhat recently. Yes, so this is a Gerstenhaber algebra, the BV algebra, and this kind of, yes, essentially, up to some details involving changing H, which I could discuss. Okay, so there's a famous structure on here, which is the following. Well, first of all, S1 acts on the free loop space by rotating the loop. Secondly, you can look at, so S1 has various subgroups in it, namely discrete subgroups. And if you take a loop and you send it to its p-fold cover, or its k-fold cover, then you identify the free loop space with the fixed points of this action inside itself, and it's kind of recursive. And this is an S1 equivariant homotopy equivalence. So this is an interesting bit of data, and it obviously has some relations with things like this, which people have worked out in part. So it leads to various algebraic structures on invariants like this. So that's something to say. Maybe let me make a remark that the free loop space is not S1 homotopy equivalent to sort of the Borel analog of this object. So if you take a space with a contractible space with a free S1 action, then this is also an S1 space, and this is homotopy equivalent to this, but there's no map back, there's no maps both ways, which are S1 equivariant, which would be S1 equivariantly contracted to the identity, because this has no S1 fixed points. So, well, this does, it's cute. Okay, so what is analog of this structure for HF? So let me tell you some things that have been done, which are interesting. So say I'm going to make say some conditions here, which I will mostly explain. So say M is Uville, which is basically those conditions. There's some class in KO1 theory of the free loop space, which vanishes. This is called the polarization class. Okay. So then, and maybe H nice at infinity, it just means that somehow grows appropriately with respect to the conical coordinate. Then there is some object this is a spectrum. Okay. And it has this property. If you take the homotopy groups of the spectrum after smashing them with Hz, then this is the Floer Homology groups of H with Z coefficients. Okay. So this is, what's a spectrum? This is like a space up to suspension. Okay, so this is this Cohen, Jones, Siegel instructions. Okay, so now, so in other words, like I just said something about spaces here. It's nice that there's something like a space that you could at least talk about. Okay. Now I will say too, this is very recent and kind of fun. So there is an analog of ES1 across HF, HS as an S1 spectrum. Okay, so this is just a spectrum, doesn't have an S1 action a priori. There is some other thing which in some informal sense behaves like a spectrum with these properties. So it's an S1 action, the S1 action is free, and for example, when you apply this object to it, you still get these homology groups. Okay, so this is by since a few weeks ago. Okay, so now I will say something that I've thought about for a long time. I will say it's a work in progress. Really not much work to do. Okay, so let me maybe make a definition before stating something. The definition. N F1 spectrum. So when you think spectrum, you should just think space up to stabilization. It's very close, and the way I think about them, I actually construct them essentially by explicit co-limits of spaces. Is P cyclotomic if there is an S1 equivalence. And we call this spectrum X, from X to its CE fixed points. And these are geometric fixed points for people who know what that is. So this notion uses some geometric model of spectrum, but on spaces, for spectra that come from spaces, it literally is just about taking the fixed points. This is a generalization of just this usual fixed point functor. Okay, so here's a work in progress. When the polarization class so this is just some bit of algebraic topology data. You have to take it in SO1 equivariant KO theory. Vanishes. Then this colimit is the homotopy. These are the homotopy groups of some cyclotomic spectrum. Or the homology groups of a cyclotomic spectrum. Okay, so let me say I have 2 more minutes. So let me say a couple words about this. So this is just, I mean, what does this really mean for a practical person? This is something that symplectic topologists study. This is called the symplectic homology. This has lots of structure. This is BV algebra, E2L, whatever you want. This pragmatically should say that it comes equipped with a bunch of interesting algebraic operations when you take symplectic homology of chaotic coefficients. And those should interact with the usual algebraic operations in the same way that these sorts of products do. And some of that is known. There are like all kinds of complicated formulas that various people have worked out. So that's practically what that means. Okay, now, so comment. This is something that took me a lot of thinking. To do this, for me, one works with non-Morse functions. So basically, what is the idea? There is this action functional AH. And what is this sharp K? This just means you iterate your Hamiltonian. So you repeat this function a couple times, you get a new function. That's the, so AH has this HK has this property that fix phi1, well, just phi1 H sharp K is the time K flow of the original Hamiltonian. Okay. And you want to then just say, well, like, let's look at the Morse homologies, or let's look at the sort of the homotopy types associated to these functions. These are all CK equivariant functions on the free loop space. The problem is that if you have an equivariant function, there's no way of perturbing it into a Morse male functions for one for which the intersection lines, the spaces of gradient flows are manifolds, without breaking the equivariance. What people usually do is they do Borel theory. They do all this kind of stuff. And that works. There's an equivariant Floer homology group. It's very useful for dynamics. But, I personally don't know how to make sense of that map while doing this kind of Borel stuff. I thought about it for a long time. There's some very interesting analysis behind why it's difficult, having to do with like certain operators looking Fredholm but not being Fredholm. You naively just want to send a loop to its p-fold cover. It turns out the analog of that, and for pseudo-holomorphic curves, is like not a Fredholm problem, although there's a formal adjoint which is like not the actual adjoint, so it's a subtle thing. But you can kind of just build this homotopy type at this bad point, at this for this equivariant function, which is not Morse math. That makes sense, it turns out. So that's the sort of technical stuff. It would be great to not need that. It would be great to just use this Borel construction, which is sort of has already been done. I mean, but without this actual map. Okay, so I think that would make my time. Yeah, but that's.
Questions?
Yeah.
So you have this cyclotomic spectrum.
Yeah.
What is its T-dis one fixed point?
So for M being a cotangent bundle, this should agree with the sort of free loop space story. So this, as a cyclotomic spectrum, will agree with the P complete. So this is a P completion. I kind of do this via finite subgroups because I don't want to do more spot theory. So this will agree with that for the free loop space. And generally, you have to compute it. Yeah, so like for a general manifold, this is not the same as the homology of free loop space. It's something you build out of all of this analysis. Okay. But, yeah. Any other questions?
Is it THH or something?
Yeah, it's supposed to be. So, okay, I mean, this is where the dreams are. So when this class, well, when the one without this S1 vanishes, so that this thing, this Uval domain, it has a Fukaya category. Maybe a wrapped Fukaya category. I'm just going to write. This is an object that's been studied. There are various theorems about it in the case where M is a Stein domain. There's a lot of work on that. And this is supposed to be just a sort of homology level shadow of some Fukaya category over the sphere spectrum. Okay? So if you took THH of this, you should get a cyclotonic spectrum. And then this is, supposed to be this object. Well, if you decompleted this. But this object is annoying to define, mainly for a lot of coherence issues. I mean, A infinity spectrally enriched categories are a miserable object that people have been struggling with for a long time. This is not a miserable object. This is actually quite concrete in the way that I've tried to work with it. So this gives you some geometric. So, I mean, sometimes your M, your symplectic manifold, is related to some algebraic variety. And in a bunch of interesting examples, this thing has like some number field of definition, maybe some parameter. And then there's some dream that people have pursued for a long time when this Fukaya category is related to some category of coherent sheaves. People have proven many instances of that. There's also these Gaussian mean connections, the variation of de Rham homology over this parameter. So these turn out to be related to pseudo-homomorphic curve theory, so to Gromov-Witten theory. But then, there's more here. There's all this arithmetic structure associated to homology. And somehow it's supposed to be related to this THH in ways that people here know vastly more than me. I had sort of some dream a very long time ago trying to come up with something that might go on this side. But at least there is some precise statement one can make in the exact case, from which one can then try to derive whatever is possible. Okay, thanks. Does that answer that question?